Okay. So let's start with a review of what we did last time. So I really like doing that. At the beginning of make a very quick summary of what was discussed in the previous lecture. So remember, in our last lecture, I talked about some general stuff first, and then I explained what this course is about. Okay, so this course is Introduction to Aircraft Performance, and we define what an aircraft is. And then I gave you this list, which are the things that we will be studying throughout this semester. Okay, so we will be studying these things. So we may skip one or two of them. Okay, so something related to this course and is the flight mechanics. So this is a first year must course, and when you come to third year, you will be taking the flight mechanics course. So I think before we start this course, I should talk about what flight mechanics is about as well. So here's the definition of flight. Flight is the process by which an object moves through the air by generating the necessary forces. Again, so the key thing here is the necessary forces for the flight to take place should be created by that device using the air around it. And classical mechanics is concerned with the set of physical laws mathematically describing the motions of bodies under the action of a system of forces. So basically in classical mechanics we study the effect of forces acting on bodies. Okay, so you know that from your physics courses. If you have a body and if you apply a force to it, that force will create a motion. Okay, so this is the science that studies that is called classical mechanics. And when you consider these two, and if you combine them together, you get flight mechanics. And flight mechanics is basically the study of the forces that act on an aircraft in flight and the way the aircraft responds to those forces. So again, you combine these two. Instead of a general body, we specifically consider aircraft, and then we study how an aircraft moves when certain forces are applied to it. Okay, so this is the study of that is called flight mechanics. And what we will be doing in this course is actually related to that. So if you go back to this list, so to be able to answer these questions, we will be using mechanics. For example, when studying the climb performance, climbing is the change of an aircraft's altitude with respect to Earth. Okay, so if you have a climbing aircraft, its position is changing. It's in fact moving. To study that motion, what you're doing is basically flight mechanics. So you need to calculate the forces, and then from there you can calculate how well it climbs. So before we start doing that, we should really understand this mechanics part. So this mechanics is really based on what's known as the Newton's laws of motion. So I know that you're familiar with these laws, but these laws are really very important. So these laws are the foundation of flight mechanics, basically. So to understand flight mechanics and to understand this course before even flight mechanics, you should be very familiar with these Newton's laws of motion. So I'm going to read you the definitions here. As I said, you should already know these laws. The first law says that everybody remains in a state of rest or uniform motion, which means it's moving. It keeps moving with some constant velocity along a straight line, unless it is acted upon by an external unbalanced force. So if you have, a chair, and if no force is acting on that chair, and if that chair is initially not moving, then it stays so, right? It doesn't move anywhere. Or if you have an object which is doing some uniform motion, it moves along a straight line with some fixed velocity. If no forces are acting on that object it keeps moving along that direction. It doesn't change that state. So this is what the first law says. Okay, so if you consider this diagram here, the forces you see here are known as the 4 forces of flight. So these are the 4 main forces that act on an aircraft. So we will be talking about these forces throughout this semester. So you know the weight. Every object on Earth has a certain weight. So the weight is towards the center of the Earth, right? So the weight force will be acting in this direction. And if you, for example, want to keep this aircraft stay in its position in the air, you need to balance this weight, which is the lift force. So you need to somehow create this lift force. And then there's a similar relation in the horizontal plane. So these 2 forces are in the vertical direction, lift and the weight. But if you have a motion, then there will be an aerodynamic drag force to resist that motion, which is this force here. And you need to balance this force as well. And that will be done by this thrust force. So when you look up in the air, most probably you will see an aircraft flying, right? Now, a lot of aircraft pass over us every day. And you see these aircraft flying along straight lines. Okay, so most of the time you see these trails coming out of their engines. You see these white lines coming out of the aircraft engines. And if you look at that, you see that they're moving along a constant line. Okay, and they move with some constant velocity during cruising flight, aircraft flight, some constant velocity. So to maintain that motion, this first law of motion should be valid. In other words, you have an aircraft flying with some constant velocity, and you want that state to be preserved. That means there should be no unbalanced force acting on that aircraft. Okay, so this is the first law. The second law says that a body of mass m subject to a net force F undergoes an acceleration a that has the same direction as the force and the magnitude that is directly proportional to the force and inversely proportional to the mass. So instead of saying all that, you can just write this expression here. This is the famous F is equal to mass times acceleration law. So this says if you have an unbalanced force, then that force will create motion, and that motion is created through this relation here. So this is the force you apply, and that becomes equal to the mass of that object times its acceleration. But you know that acceleration is the time rate of change of velocity, or it's equal to the second time derivative of its position. You have an object, let's say you have an aircraft, it's just staying at rest at the airport. On the runway you have an aircraft that's not moving yet, and you want it to move. So that means you want it to have some velocity, and to obtain that velocity you need to apply a force. And whenever you apply a force, the acceleration will be given by this relation here. This is the second law. And the third law says that the mutual forces of action and reaction between two bodies are equal, opposite, and collinear. This means that whenever a first body exerts a force F on the second body exerts a force minus F on the first body. F and minus F are equal in magnitude and opposite in direction. So this is the third law. So this is also known as the action-reaction principle. So this is also very important, especially when we discuss aircraft engines. You will see that this is for even the lift force, the aerodynamic forces, the foundation of all the aerodynamic forces is actually this law. So that means, so if for example, I'm applying a force to this desk, right? I'm just pushing on it, and the desk applies the same force back to me. So I feel, as I push with my hand here, I feel the same force on my hand. Again, so this force is also very important. So these three laws are the base of everything. So remember, in our last lecture I said we will be calculating all these things using some simple equations, and you will see that those simple equations come from direct these Newton's laws of motion. So I'm hoping that you're already familiar with these laws of motion, but still I think you should really spend some time to think about these laws, and I at this point suggest you this course at MIT. Let me try to find that. So anyway, I cannot really find that for a course here directly. Let me try this one. So anyway, I will provide you that link later on. So this professor, as I mentioned about him before, so he has a very good way of explaining lectures, and he has a 1-hour lecture on Newton's laws of motion. I will give you the link, and I strongly suggest you that you watch that course. Okay, so he talks about these laws of motion, and as I said, everything we will be doing in this course is based on these 3 laws of motion. So you should definitely watch his lecture, and then hopefully it will help you understand the following lectures better. So again, now I'm really curious why I couldn't find this course. Well, anyway, I don't think it's really worth our time now. Okay, good. Now, okay, so if you look at this diagram here, for an aircraft to keep flying in the air, you need to somehow create a force which will be cancelling the effect of its weight. Okay, so you need this force in the vertical direction, and I said that there are basically 3 different ways this force can be created. And then we talked about the static lift concept, which basically uses the buoyancy principle, and then these are the aircraft that use this principle are in general called LTA aircraft, which means lighter than air. And then there's this dynamic lift concept, which is what actually most aircraft use. And this is the only thing we will be considering, by the way. So in this course, we will focus our attention to aircraft that use the dynamic lift concept. There will be nothing related to this LT aircraft in this course. And then there's the 3rd way of creating that, which is the direct thrust force from the jet engines. There are just a few aircraft that use this concept, and I have a video of this F-35 aircraft. Let me show you that. Okay, so this aircraft is on the runway. It's stationary, it's not moving. Okay, so now it starts climbing, right? Slowly, but it's climbing. So at this point, obviously, the weight is balanced by some forces, and these forces are coming from its engines directly. So this is neither the static lift concept nor the dynamic lift. So what's happening here is, so as you see here, it directs its engine output in the vertical direction, so that and then there's something in this area as well that we cannot see. So by creating these forces, it starts moving, and this is the thrust force concept. Okay, so this is really out of our interest, really. We don't really, we will not be talking about this vertical thrust aircraft at all in this course. So everything in this course will be about aircraft which create the dynamic lift. So we'll be talking about, okay, aircraft like this. Okay, so before proceeding further, I would like to start talking about the elements of an aircraft, the parts of an aircraft. So let me open that slide. Okay, so in flight mechanics, we consider motion of aircraft, okay? And we live in a three-dimensional world. And when we talk about flight mechanics, we're talking about the motion of an aircraft within this three-dimensional space. So in this three-dimensional space, we can define a reference frame. So you need three axis systems to define the position in this three-dimensional space. So you choose X, Y, and Z axis. So the motion means that the position will be changing with respect to this reference frame. So I guess I can just skip this degrees of freedom business here. Okay, so now let's talk about how this is achieved, how we control the motion. Okay, so you have a three-dimensional space, and you have an aircraft that you would like to move within this space. So it can go along these three axes, it can go up and forward and backwards along these three axes, and then it can rotate around these axes. So there is the motion it can have is translation along these three axes and then rotation around these three axes. But for regular aircraft that use dynamic lift concept, there needs to be a constant forward motion. In other words, for this aircraft to be able to stay in the air, it should be moving along X direction at all times. So I will be talking about this next week. But for now, let's just assume that this fact. So it needs to have a constant motion along X direction. So there's no other way of doing that. If you stop that motion, then you cannot create lift force and your aircraft will just crash. So it needs to be moving at all times. You cannot keep a regular aircraft stay fixed in the air. Okay, so then what you do is, if you want to go up, for example, if you want to move along the Z-axis, which is the climbing axis, you cannot really move an aircraft directly along that axis. So let this be an aircraft, okay? So this is the x-axis, it needs to be moving at all times. So you cannot really move it along z-axis directly. So what you do then is you rotate it first, okay? And then its motion becomes, its velocity gets a component in the vertical axis. That's how you get the climbing motion, if that makes sense. So if you have this aircraft that's in constant motion, if you want to climb, you rotate it first, and then it starts going along a line which has a vertical component. So this is basically what you do. Okay, so if you want to go up or go down, you do this rotation first, and then your velocity vector will take you in the direction you want to go. Does anybody here know the name of this motion, this rotation that you see on the screen? That's right, this is the pitching motion. And then if you want to go sideways, the same thing is valid there. So if you want to go along this y-axis, for example, you don't move the aircraft direct along that axis. So you do what you do in the other axis. You first rotate your aircraft, and then once you rotate it, its velocity vector will be in the direction you want to go. Okay, so this is how we control regular aircraft. So this is not the case for helicopters, by the way. If you have a helicopter, you can just make it go sideways, or you can make it climb without having to point its nose up first. This is the yawing motion. It's the yawing axis. And then there's this rotation around the last axis, and this motion is called the rolling motion. Okay, so all of these is possible by changing the forces accordingly. For example, if you want your aircraft to rotate around the pitching axis, you need to somehow arrange the forces such that these forces will cause a rotational acceleration around that axis. Okay, so this is true for all axes. So whenever you want to make a certain maneuver with your aircraft, what you need to do first is you need to create the forces that will give you that motion. Okay, so we will be talking about how these forces are created and how they are manipulated. Actually, you already see on these animations, if you pay attention here, for example, here you see that these little black pieces are moving up and down, and they create this motion. And then for this motion, this piece is moving, as you see in this animation, and then you have these other devices moving. Okay, so in this course, what we'll be talking about is valid for conventional aircraft. So I'll be using this phrase a lot during the course. I'll be saying for a conventional aircraft, and by conventional what I mean is just typical, regular or normal. So you see two examples of conventional aircraft. So these are the aircraft that you know, right? So if I ask you to draw a picture of an aircraft, I'm sure most of you will draw something very similar to this, right? You will draw wings here, and then you draw these little wings at the tail of the aircraft, which we call the tail surfaces. And then there's this tubular shape, which we call the fuselage. So these are, this is a different aircraft, obviously, but it has the same main components. Okay, so it has just wings, just like this one here. It has, its wings are shaped differently, but nevertheless it has a pair of main wings. Similarly, it has some tail surfaces. Even though it looks different, they are both conventional aircraft. They have the same components. Now let's take a look at some examples of unconventional aircraft. So the aircraft you see in these pictures are unconventional. You know, they have different shapes. So when you look at this aircraft, it looks different because it has these relatively large wing surfaces at its close to its nose. So these wings make this aircraft unconventional. Or if you look at this aircraft here, you see its engines, its propellers are pointing at a different direction, and in fact these can rotate. Okay, so these propellers can be placed to create a forward force, or they can be placed to create a vertical force. So that's what makes this an unconventional aircraft. So this aircraft is also looking different. It has these wings in the front rather than at its tail. Also, it has a wing which is leaning forward. So when you consider conventional aircraft, the wings are leaning backwards. Okay, so this is called the sweep angle. But if you look at this aircraft, it's the angle of its wings is pointing forward. So this is another unconventional design. It's in fact a very interesting design, but This doesn't have an engine like a regular aircraft. So this aircraft has a propeller at its front, providing thrust force. This has two such propellers. This has a jet engine, but this doesn't have any of that. It doesn't have a propeller, or it doesn't have a jet engine, but instead it has this part along its wings. So what you see here is providing its thrust and lift force. So anyway, these are unconventional aircraft, and they have different mechanisms, but we will not study these aircraft in this course at all. So everything I will be talking about in this course will be valid for a conventional aircraft. Okay? Any questions? Okay. Now let's talk about the main elements of a conventional aircraft. Let's start with the main body of an aircraft. It's called a fuselage. A fuselage is the body of the airplane, which is basically a long hollow tube which holds all the pieces of an airplane together. So all the other elements are attached to the main fuselage. It's in the center, and it carries whatever you want to carry. So if you have a passenger aircraft, then the passengers will be sitting in its fuselage. Or if you have a cargo airplane, then your cargo will be stored within the fuselage. And again, the other parts are attached to this main part. You see some fuselage examples here. So this is a cargo airplane. It has this really large and long, big fuselage. That's because you want to carry large cargoes. So you can fit really large parts within this fuselage here. In fact, this is the largest airplane that has ever flown. And it's still flying today. This is Antonov 225. Let me see if I have, no. So anyway, there's just one. They built two of these airplanes. It's a Russian airplane, Antonov, and only one of them is flying. It is still flying, and there's just one airplane. And again, this is the largest aircraft that has ever flown and is still flying. So this is F-16. So its fuselage is this thing here. So if you compare these two, they are quite different. You know, this is very large. It has a very large diameter, and then it's really long. But this is much smaller compared to that. But again, they're both called fuselage. So it has a different, varying cross section. For example, if you take a cross section here and another cross section here, they are very similar. So the shape of the cross section of the fuselage is very similar along this direction. It is not the case for this one. So at this point, it has a different cross section. So let me just try to. For example, if you take a cross section here, what you will see probably will be something like this. You see this place here where the pilot sits, and then it will be something like that. Or if you take a cross section here, it will be more like, it will be wider. So as you see, the cross section keeps changing. And this is the SR-71 airplane. This is its fuselage. You see it has these sharp edges around here. So compared to this, it has a very different shape, because it's a very round cross section. This aircraft has a very round fuselage with a round cross section, but this one has these sharp edges. Okay, so so let's take a look at this one. Again, this is a cargo airplane, and the goal is to have the fuselage as large as possible. So they designed this aircraft. And then there's this thing here, which is an example of an unconventional aircraft. So this is probably the funniest looking aircraft that has ever been designed and manufactured. So it's a German design. In fact, there are videos of this aircraft on YouTube. I may have it here on my computer as well. So they actually made this aircraft and designed it, manufactured it, and it was flying, but then they canceled it. So I guess in this aircraft you would call this part the fuselage, so because this is where the pilots sit. And then it has this other part, I don't know, I think this is a fuselage as well, I'm not sure. It has one propeller here. So this has the obvious advantage that in a conventional aircraft with a single engine, the propeller will be in front of the fuselage, right? And it distracts the pilot's vision. So if you have a conventional aircraft with a single engine, so I don't think I have. Anyway, so the pilot will be seeing the propeller rotating in front of him. But this is not the case for this one. So the pilot has a very clear view. They made this glass front here so that the pilot can clearly see what's happening in front of him. Okay, so the next element of an aircraft is the cockpit. Cockpit is a compartment in which the pilot of an airplane sits. So this is the cockpit of this aircraft. This is an F-16, the two-seater version. So two pilots can sit in this aircraft. So this is the fuselage. And this is a passenger airplane. And this is the cockpit of this airplane. The pilots sit in that area. So the inside of a cockpit, so this is the cockpit of a glider. It's very simple, as you see. There are just very few displays here, so the pilot can use these things to check the operation of his aircraft. It's relatively simple. You know, there's this stick here. The pilot uses this thing to control the aircraft, and there are some pedals here. So he pushes these pedals with his feet to control the aircraft. So the cockpit can be as simple as this here, or it can be as complex as this cockpit here. And this is the cockpit of the Airbus A380 aircraft. So these are both regular or conventional airplanes. They are both called cockpits, but as you can see, they can be very, very different. So in this case, you see it looks like there's a bunch of computers put together, right? So you have a lot of computer displays here showing different things. And then the pilots have these keyboards in front of them. And they have these joysticks to control the airplane. Okay, so if we move along with the elements of a conventional airplane, then the next thing we talk about is the engines. So every conventional aircraft needs to have, well, every aircraft, conventional or not, needs to have some sort of thrust force. So here we see a jet engine. The objective of this device is to create the thrust force, which is necessary to keep the aircraft moving forward. This shape is called nacelle. Well, you have the engine which is inside here, and the nacelle is the structural part that holds the engine. So it's this circular structure. The engine is inside that part, and then this part is called the pylon, and the pylon is the part which attaches the nacelle to the wing of an airplane. Okay. These are the wings. Again, you see two very different wing designs. Again, these both are conventional airplanes, and they both have wings, but the wings don't really look anything, they don't have too much in common. Wing is a surface used to produce lift for flight through the air. Okay, so this is the part that creates the force necessary for flight. So if you look at the wings of this aircraft, they are relatively small and they have this trapezoidal shape. But if you look at this airplane, the wing is much longer compared to this one here, and it has a different shape. It's not exactly like a trapezoid like this one here, but it has this curved shape. So again, the wings are the main force generating components of an aircraft. So the lift force which is necessary to carry the aircraft is created by this. So this aircraft has a weight, and then the lift is created by these wings. Okay, so this wing will be creating a lift force, and the other wing will be creating a similar force, and when those two forces come together, they carry the weight of the airplane. So this has the same purpose, obviously. So this will be creating the lift force to carry the entire weight of the aircraft. And the reason that it has a different shape is just to make it more efficient. Okay, actually, a lot of study is behind this shape. So this is the Boeing's newest design, Boeing 787. They call it the Dreamliner. And the benefit of this airplane with respect to the previous designs is that this is more efficient. It burns less fuel. So to go from Ankara to Istanbul, I don't know, it requires so much fuel with the previous design. Well, this one, it consumes less fuel. And the main reason is its wing design. They designed a wing such that it creates the necessary lift force to carry the weight while creating less drag force. Anyway, so I'll be talking more about these lift and drag forces later on. So let's take a look at some definitions about wings. As I said, wings are the main force creating parts. Okay, so let's come back here. Some forces will be acting on the fuselage, and some forces may be created on even these nacelles, but these forces are really small forces. Okay, so you can just ignore all these forces because they are much smaller with respect to the force created here. So remember, in our first lecture I told you that we will be calculating an aircraft performance, and then we will be using some simplified equations. And one of the first simplifications we make is we just take into account the force created by the wings, and we ignore the other forces. So this is one of the assumptions we make to make simple equations. So otherwise, as I said, some forces are obviously acting on every part of the aircraft. But since the forces on the wings are so much greater with respect to other forces, this is what we will be studying only. And to be able to study these, the forces created by the wings, we need to somehow take the shape of the wing into account. And to be able to do that, we need to define certain things. Okay. So, for example, we have two different wings here. So this is one of them, and this is the other one. This is the other one. So obviously they are very different. But how different they are? So we need to put these differences into numbers. Remember, so this is related to what I said in our previous lecture. In everything we do, we need to use, as engineers, we need to use some scientific equations. And in these equations, we need some quantitative information. We need some numbers. And to put this shape into numbers and put this other shape into numbers, we need to define certain properties. And these are the main parameters used to define a wing. So here we're looking at a conventional aircraft wing from the top. So as you see, this is the top view. So the fuselage will be here, for example. Okay, so this will be your fuselage. Anyway, so I think I can just remove these. Let's see. This part, which is the front edge of your wing, let me just draw it here, is called the leading edge. So this is the leading edge of the other wing. Okay, and the back edge of the wing is called the trailing edge. It's your trailing edge. Okay, and the amount of force created is related to how large your wing is. So if you have a small wing, obviously you get a small force. If you have a large wing, you have a large force. This is very, I think it's very reasonable. And what I'm trying to say is the total area of the wing is a very important parameter for our calculations. So we call this the wing surface area. This is this thing here, wing surface area. So that's another parameter used to define a wing. And then we call this distance, which is the distance between the left wingtip and the right wingtip, is called as wingspan. And the small case letter b is used to represent the wingspan. Then the distance between the leading edge and the trailing edge is called the chord length. As you see, that's not a fixed number. So if you calculate the distance between the leading edge and trailing edge here, it's this much. And this is the chord length at the tip of the wing, which we call tip chord. So this is also a chord length, but this is the chord length at this position. It's a different number. And the chord length at the center is called the root chord. So it's different. So for our calculations, instead of using these varying chord lengths, we use a single chord distance, and that is called the mean aerodynamic chord. Okay, so again, so the chord length is not a constant number, so it has a different value here, it has a different value here, a different value here, so you have these changing chord distances for this wing. But instead of using all these changing chord lengths, we define a certain chord length, which is just one single number, and that is obtained geometrically, as you see here. So let me just clean up this a little bit. Okay, so what you do here is you take this length, you take this root chord and put it here. Okay, so this has the same length, and then put it here as well. Then you take this tip chord and put it here. So this has the same length as this tip chord, and then you draw these two lines to connect these edges. So you connect this to this part here, and then connect this thing to here, and they intersect at one point, and the chord length at this intersection point is defined as the mean aerodynamic chord. Okay, and then we use these numbers to differentiate wings, different wing designs. A very important parameter that I will be talking more about in the future is the aspect ratio. This is abbreviated as AR, and it is the ratio of two things, the ratio of B square to S. Remember, B is the wingspan, which is a distance. So this B has the unit of meters, for example, and then B squares is meter square, and S is an area which also has the unit of distance squared. So the aspect ratio is a dimensionless number because you divide a term with the unit of an area to another term which has the same unit of area. So when you do the division, it becomes a dimensionless number. For some reason I cannot really delete this. Anyway, so the aspect ratio tells you how long and slender your wing is. So for example, so let's consider these two wings. So the the difference between, they both are in the shape of a rectangle, and the difference between the two wings is expressed by using this aspect ratio number. Okay, so this has a large wingspan and a certain area, whereas this has a much smaller wingspan. So this is the wingspan of this wing, and it has an area as well. So since this has a much lower wingspan compared to the other one, it will have a small aspect ratio. Where did it go? So let me just draw it again. So this is a high aspect ratio wing, and then this is a low aspect ratio wing. Okay. Anyway, I think our time is up, so let me just stop here. Okay, so there are just a few things I would like to continue about the elements of an aircraft, and then on next Tuesday I will start talking about how this lift force is created. Okay, so I will see you on Tuesday.